So we have been discussing about this micro assembly. So in fact, we had discussed about the various aspects of micro assembly, especially related to this influence of scaling laws. So we had also discussed about the different source and applications of these micro assemblies, then these electrostatic forces which are involved, and then appropriate configurations of these micro assemblies, then overall capillary interaction of these micro assemblies, role of magnetic and micro assemblies, and there is a comparison between a direct assembly versus traditional assembly, how these has been deployed, and then we have also discussed some of the case studies related to this micro manipulation, and then we also had some discussion about the different challenges which are involved in this micro assembly. Now in today's lecture, so we will discuss about this micro aerial vehicles. So as far as these micro aerial vehicles are concerned, so most of us are fascinated by this micro aerial vehicle, especially like when we talk about these micro drones, etc. So these micro drones has a potential application in defense with reference to space. In fact, it is completely involved in some kind of inspection of tubes, pipelines, AC ducts, etc. in detail. So as far as these, when we try to configure or when we try to define these micro aerial vehicles, these micro aerial vehicles are small unmanned aircraft designed for resonance and surveillance and other specialized tasks. So if you try to look into the overall size of this micro aerial vehicles, so they typically range in the size from few centimeters to around 50 centimeter and be controlled remotely or autonomously. See, these micro aerial vehicles are widely used in defense related, especially in strategy related areas, commercial and research applications. It is mainly due to their agility and ability to operate in a kind of a confined space. Ideally, like we might have heard a lot about these micro aerial drones, etc. So they can work in a confined space and appropriately they can give a kind of a input to the system, or like they can cater the required functionalities for different strategic related applications. In fact, it has a wider spectrum. So micro aerial based electronic systems are there, then micro aerial based structures are there. So those can be appropriately deployed. So now, as far as these micro aerial vehicles are concerned, like the one of the key elements of micro aerial vehicles are the wings. So ideally, if you try to consider a drone, so you have a kind of a fan kind of structure. These fan rotates, then appropriately you can see the motion. Whereas in the case of a wing, so the flapping wing of the micro aerial vehicle is concerned. So as far as in these wings are placed, so these wings flaps at a very high frequency, and based on the frequency, so appropriately we can use it for different requirements or different applications. So like when we try to look into the overall definition of this flapping, so the flapping or beating motion of wings is exclusively used in the powered flight of a bird. So that's why I have integrated two GIF file over here, which basically says that how a flapping wing can be helpful for an appropriate aerodynamic motion. So basically these, so they are meant for powering the flight of the bird and insects to counter the gravity force and propel themselves against the kind of an aerodynamic drag. So when we try to quantify such kind of flapping, so the mode and the frequency of the flapping motion differs among the different species and are strongly dependent on the body size, shape and the flight mode. So they are, however, always selected for the optimal power consumption of the respective flight modes. So the difference between the flapping motion of a bird and insect is in the way they use the aerodynamic force for the lift and the drag. So ideally, based on the lift and the drag, appropriately we can establish a kind of a flapping motion of the bird. So like in this particular case, especially in the case of birds, so technically we can consider the Reynolds number. So these Reynolds number D is Reynolds number, which is the ratio of the inertial force to the viscous force, and the wings aspect ratio are so large that they deliberately use their wings to sustain their weight by lift. So with large wingspan and high aspect ratio, they can achieve a kind of a long range flight. So that is considered to be one of the key aspect of this microassembly robots. Now, if we so whenever we are trying to design such kind of micro aerial structures or micro aerial robots, some of the key parameters which we may need to look into it. So one of the key parameter is something like a kind of a flapping wing MAV. So in this, like, there is a Reynolds number and the aspect ratio is too small to provide the necessary lift. Now if we try to look into the different process parameters which are available, so one is the net force, then we have the downstroke. Okay, so this is a kind of a movement of the flapping MAV. So in this flapping MAV, we have two net forces. One net force is in this particular direction and the other net force is along the median of the direction, and then there is a downstroke which exhibits over here. So in this downstroke, so appropriately there is going to be a movement. Okay, now as far as in this particular case is concerned, there are two sets of motions are there. So one is called as a pronations motion, another one is a upstroke, and the second one is called as a supination. Okay, so these are considered to be the different motions which are exhibiting in the case of a flapping wing of a MAV system. So like in insects, let us consider the earlier case when we try to look into the Reynolds number. So the Reynolds number which for a bird perspective point of view, it will be different, and with reference to insect perspective point of view, it will be different. So in the case of insect, the Reynolds number and the aspect ratio are too small to provide the necessary lift, but they owe much of their extraordinary evolution success to flight, because their survival and evolution depends on crucially on flight performance, different flight related sensory, psychological, behavioral and biomechanical traits. So these are some of the key aspects which we may need to consider. So the flapping motion of an insect can be decomposed into three separate motion. One is called as a sweeping or a flapping. So sweeping or flapping is nothing but forward and a backward movement of the wings. Heaving is nothing but up and down movement, and pitching is nothing but changing is in the incidence angle. Now let us see this particular figure. So as far as in this particular figure, this figure is a schematic representation of a left wing motion of an insect, which is shown over here. So a complete flap cycle for a sophisticated insect wing motion consists of twice a translation, that is a downward stroke and an upstroke in this direction. Okay, and twice the rotation. So basically these termed pronations at the end of the downstroke and supination at the end of the upstroke. So this is a kind of a pronation which is scattering the upstroke, and the supination at the end of downstroke. So during the translation, the wing may show a kind of a sweeping, heaving and pitching motion. In addition, at the end of the half stroke, during the stroke reversal, the wing pitches rapidly and the exact wing kinematics varies among the different insects for different motion in flight. So that's how we try to introduce these parameters of pronation and supination, which is one of the key parameters for designing any kind of system. So now in this particular case, so insects have generated a great deal of interest among the biologists and the engineers because of its biomimicking capability, because at its first glance their flight seems to be improbable using a standard aerodynamic theory. So that we have observed, like in most of the cases they don't follow the aerodynamic theory. However, when there is a kind of a stabilization happens, appropriately it tries to pitches and aerodynamic theories are established. So the combination of small size, high stroke frequency and a peculiar reciprocal flapping motion of the insect make their flight aerodynamic and unintelligible. So if we closely observe these micro aerial vehicles, so these micro aerial vehicles are small unmanned aerial vehicle of size less than 15 centimeters. So of course, now you can imagine almost your sensor should be also within that particular domain. Your actuator should also be in that particular domain. Your entire feedback system should be within that particular domain, and appropriately we can develop a kind of a small onboard chip appropriately. So like as far as in this particular case is concerned, so these MAVs are not smaller version of larger aircraft. They should be seen as a kind of an aerial robot having more degrees of freedom and agility than the regular aircraft, which puts them in a class of their own. So actually it is something like once you have more degrees of freedom, so appropriately you can have an improvement in your agility, and then it acts as a kind of a regular aircraft. So whatever disturbance or whatever kind of noises which are generated, so appropriately it can be countered owing to its agility as well as with reference to the flapping characteristics. Now, when we try to look into the features of MAVs, so as I discussed earlier, one important feature is a kind of a small and a lightweight. So of course, when we are trying to use such kind of aerodynamic structure for the movement, etc., so it is expected that the system will be of small and it is of lightweight. Second important point with reference to these MAVs are they should be electrically powered. So like when you try to power up, so appropriately you can see a motion. Then it should be a kind of a bio-inspired design. So as far as in this bio-inspired design is concerned, like it talks more about its capability in such a way that, say, once you have a bio-inspired design, so appropriately, like what happens is there will be a kind of a flapping behavior which exists. Owing to its flapping behavior, appropriately we can expect a motion. Then we have a kind of a real-time communication. So as far as in this real-time communication is concerned, so there will be a kind of a which is considered to be one of the key aspect in today's drone technology, like especially when you are talking about this micro aerial vehicles for a kind of a span kind of arrangement or a kind of group of systems kind of arrangement. In those conditions, such kind of real-time communications are required so that they start communicating with each other for an appropriate motion. And as I had mentioned earlier, one of the important capability is the autonomous capability. That is, in some cases they may need to work on the group, or in some cases they may need to take a swam. In some cases they should have an autonomous capability in such a way that their feedback can move in an appropriate direction so that they can have a motion getting come out of it. So ideally, like when you try to closely observe these features, so these features play a vital role towards development of this system. So especially like if I try to converge this, powering will cater the actuator and the sensor. It has a direct relevance towards the power capability. Then when we try to talk about the real-time communication, so the communication happens between two different bodies, so appropriately you can have a kind of a movement. And then there is a kind of an autonomous capabilities. So as far as in this autonomous capabilities are concerned, so it is something like this, like when a system is integrated, so you will be having a kind of a it has its own decision. So ideally, like since it has its own memory capability, so it can cater its own decision for appropriate movement or appropriate motions, etc. Now as far as bio-inspired design perspective point of view, it itself is a separate study, because with respect to bio-inspired design, so what happens is, like once you try to get the design from a biological perspective point of view, it has its own challenges in implementation. However, with reference to functionality perspective point of view, since it is already a proved system, so it is so by implementing it, we can have a appropriate ease in motion as well as a flexibility in the overall process. Now let us discuss about the different types of this micro aerial vehicle. So as far as the types of micro aerial vehicles are concerned, so we can classify these micro aerial vehicles into three types. One is called as a fixed wing micro aerial vehicle, another one is called as a rotary wing micro aerial vehicle, and third one is called as a flapping wing micro aerial vehicle. So ideally, if we try to look into this classification, the entire classification of this micro aerial vehicle depends upon the overall capability, especially the overall movement as well as the overall wing capability. Okay, so in some cases we can have a fixed wing type, in some cases we can have a rotary type, in some cases we can have a flapping wing type. Now, as far as this fixed wing type is concerned, these fixed wing micro aerial vehicle, also known as micro drones, may be defined as a kind of a inhabited micro aircrafts capable of completing surveillance or recognition mission in outdoor or indoor environments. Okay, so this is one of the key aspect with respect to fixed design micro aerial vehicles. So this is a kind of a fixed design micro aerial vehicle, which is a kind of micro drones. Almost it looks like a kind of an aircraft, and it is capable, and it is used for wider application. As far as in this particular case, the wing design is crucial, with factors like platform, aspect ratio, camber, which influence the aerodynamic performance. So when we try to look into the overall wing design perspective point of view, like it has to withstand both the drag as well as the lift. So appropriately the ratios are entertained. Now, like as far as in this particular micro assembly of, as far as in this particular micro aerial vehicle, propellers are commonly used, so for thrust generation, and the interaction between the propellers and wings can enhance the lift and stability, especially in configuration with counter rotating the propellers. So what happens is, when there are propellers which exhibits, so based on the motion of the propeller, so you can have a lift and a stability, and then you can have a kind of a counter rotating propellers which exhibit over here. Now in most of the case it is used in mapping, it is used in surveillance, and it is also used in the kind of a disaster response as and when it is required. So these are some of the major characteristics with respect to fixed wing micro aerial vehicle. So this is the second type, which is called as a rotary wing micro aerial vehicle. So as far as in this rotary wing micro aerial vehicle is concerned, so we have rotors in place. So these rotary wing micro aerial vehicle are small. They are unmanned aerial vehicle that uses rotor blades to generate lift and propulsion. They are particularly useful for mission requiring hovering, maneuverability, and in tight spaces, and vertical takeoff and landing capabilities. So ideally this is used for vertical takeoff and landing capabilities like VTOL capabilities, etc. So in most of these cases, so these systems are kind of a radio controlled 4-rotor aerial vehicle with 4 channel of input to control the motion of micro aerial vehicle. So basically it depends upon, so wherever we want to have a kind of a varying speed of the 4-rotor, the motion can be appropriately controlled. So in this particular case, we have these let us consider we have 1, 2, 3, 4. So 4 propellers are there. Propeller 1 and 3 and 2 and 4 turn in the opposite direction. So like it is almost like by controlling individually these propellers, so we can have a control over the overall flight motion, as well as we can also have a control over the overall movement of the system. So the rotors turn in an opposite direction, which removes the need for a trial rotor, so for a torque compensation purpose, and makes the helicopter lot more compact. So the rotor turns in opposite direction, so this will help for the rotor movement. So typically a coaxial micro aerial vehicle uses the residual torque due to the angular speed difference between the 2 rotors to rotate the helicopter vertically, left or right. So increasing or decreasing the angular speed of the rotor simultaneously permits the climbing and the descending of this. So these are some kind of micro drones which are almost seen in several applications and several systems. So individually controlling such kind of rotors will be helpful for us to have a control over the angular speed, as well as to have a control over the vertical movement of it. Okay. Now, as far as these, the third type is a kind of a flapping type. So flapping type we have already seen earlier. So as far as this flapping type is concerned, it is more to do with the up and down motion. That is, wherever we have a higher frequency, appropriately we can have a movement which exhibits over there. Okay, now let us discuss about some of the key characteristics of this micro assembly. So as far as this like when we try to quantify these micro aerial vehicles, so we can just quantify these micro aerial vehicles with reference to the kinematic frames as well as with reference to the dynamic frames. So with reference to the kinematic frames, so appropriately we try to incorporate the movement, and with respect to dynamic frames, appropriately we try to incorporate the movement. So in the case of a kinematic frame, so appropriately we may need to solve the kinematics to get the overall like rigid body dynamics as well as the overall system description. Okay, so let us discuss about the kinematic frame, the dynamic frame, and the overall like flapping wing based micro aerial vehicles with reference to its performance and its details in the upcoming class. Thank you.